We say an RLC circuit will be in resonance when the inductor and the capacitor are matched. That means that the voltage on the capacitor and the inductor are equal and opposite, and this allows for the overall phase of the voltage to be the same as the phase of the current of the circuit. So this has very practical applications, as we saw earlier on, because what this means is that all of our power is working power when we have it in resonance. We're not backfeeding any power on the line, and we're getting all the energy that we need from the grid. So if we look at our phasor diagram again, we can see the voltage across the inductor for an RLC series circuit, the voltage on the capacitor, and the voltage across the resistive load. Now, the overall voltage is going to be some combination of these three vectors. And in this case, we can see that the voltage across the inductor is greater than the voltage across the capacitor. So what we tend to see here is that the voltage would be rotated, the overall voltage would be rotated a little bit in the counterclockwise direction with respect to the current. Now, if we can make this equal and opposite to this, we can make the voltage across the inductor equal and opposite to the voltage across the capacitor, which happens when the inductive reactance and the capacitive reactance are equal to one another, we will get the resonance condition. And again, power factor is very, very important in terms of this. Matching our capacitive and inductive reactance eliminates that non-working or that imaginary power load where we're backfeeding energy onto the grid and requiring the grid to actually take more power than we can actually use. So we look at an RLC circuit in terms of a basic differential equation, much like we did with a driven harmonic oscillator. And we can see here is our voltage across the inductor, which gives us this equation right here. Remember that the voltage was equal to the self-inductance times the rate at which the current changes. The rate at which the current changes is equal to the second derivative of the charge as a function of time. Our voltage across the resistor or resistive load is very simple. It's just V equals IR. I is dQ dt. And then finally, our voltage across the capacitor depends on how much charge we have on the capacitor divided by the capacitance. So we take these three elements, put them onto the left-hand side of the equation. We take a driving voltage from some AC source. This could be from the grid, perhaps. We get it on this. This is the exact same equation that we got for the driven simple harmonic oscillator with damping. And the solution to that is, is a very common one that we see in differential equations. But the main point here is that when we solve this and we get our equation for what the charge is doing at any time, we can then use that to find what the current is doing. And again, we get our maximum amplitude in terms of along the resistor when we are at resonance, because the capacitor and the inductor are balanced. They're basically trading energy back and forth with their electric and magnetic field. We can see in the equation for impedance that when XL is the same as XC, those are the reactances for both the inductor and the capacitor, that this term basically goes away and all of our impedance just becomes due to our ohms from our resistor, our ohmic losses here. And again, if we're looking at the phase angle between the voltage and the current, we get this equation right here, where again, XL minus XC, if that's equal to 0, we're basically going to have a phase angle of 0. We're in resonance. So again, here's our phasor diagram. We can say that this diagram right here can be reduced to this diagram right here. Here is the voltage across the resistor. Here is our current right here. Here's our driving voltage. And VL minus VC is going to be this vector minus this vector. And again, this phase angle will really be determined by how large this voltage difference is, how large the reactance difference is, okay, divided by how large this voltage is right here. All right, I should say the tangent of that angle is going to be equal to that. So again, if we can either reduce our, our voltage here, which is reducing our inductive reactance, or improve our voltage here, increase our voltage here, which is our capacitive reactance, again, we can get a balance and we can bring this vector and this vector closer to one another. We can take this vector, really, you can think of that as sort of rotating it toward the voltage across the resistor, getting this closer to the resonance. So again, we want to sort of do this. We know that with a large inductive load, if we add a lot of capacitors, we can boost VC here, which is going to make this summation vector smaller and smaller. And again, it's going to get this angle smaller. And that's going to make our power factor higher and higher. Remember, our power factor is how much power, working power we have divided by the overall power. So when we're not at a power factor equal to 0, there's a small amount of power that we're feeding back on into whatever our AC power source is. And that either has to be corrected for on site, or it has to be corrected for by the power company, usually back at a substation where they need a bank of capacitors. And again, here is the condition where VL minus VC is 0. This is resonance, and both the current and the voltage are in phase, which corresponds to 100% working power. If we look at the overall current in this circuit, the RMS current, this peaks at the resonant frequency because that is where the impedance is the lowest. Again, remember, impedance is telling you how much voltage I need to get a particular current. So if I reduce my impedance to its lowest value, I'm going to get my greatest current for a given voltage when the impedance is the lowest. When we look at this condition, if we set XL equal to XC, we get that the inductive reactance is equal to omega L. The capacitive reactance is equal to 1 over omega C. I can take omega and multiply it by both sides, divide both sides by L, and we very easily get our condition for resonance. So the resonant frequency, again, just like our driven harmonic oscillator, it's going to oscillate the greatest at its resonant frequency. Here, we're going to get the greatest current flowing through the circuit at its resonant frequency. For a harmonic oscillator, we know that happens when our omega is equal to, I gotta think about this, the square root of, the square root of K over M. Here, it's going to be 1 over the square root of L over C. So let's take a look for a typical AC source, plugged into the grid. It's operating at 60 hertz. Basically, if we want to balance our inductive load, again, let's say we're running a lot of air conditioners or we're running a lot of large electric motors, we want to balance that inductive load, we can say that the capacitance that we need is going to be equal to 1 over 4 pi squared. This 4 pi squared comes from the fact that we've converted omega into 2 pi f, 2 pi times the frequency. The frequency is 60 hertz. L is our inductance, and of course, we are looking at that when we have a condition for our capacitance is balanced with our inductance. All right, let's do an actual application here. Let's say we have a 350 millihenry inductance in a motor. What capacitor would we need to balance this phase? It's important to note here that the inductance of a motor actually changes depending on, if it's operating or it's just starting up. Generally, what happens is that when it's first starting up, you're going to have a much higher inductance. But let's say that when the motor is operating at its operating speed, it operates at 350 millihenries. What capacitor would I need to balance that phase so I have a power factor equal to 0? Well, again, you can just plug into this equation right here, and we get a fairly small capacitor, 9.34 millifarad capacitors. So again, theoretically, if the resistance is 0 for an AC circuit in resonance, it would go to an infinite current. We know that all practical devices have some resistance to them. And we can also use this idea of resonance for a radio. By using a variable capacitor, we can say, instead of plugging into the grid, we are using an antenna, which is basically picking up induced voltages from radio waves. And by tuning the capacitor and the inductor is basically fixed. It's a coil wrapped around the antenna, for simplicity's sake here. If we get the capacitor to match the inductor at a particular frequency which is being broadcast, we can use that fact that will maximize the current at resonance. Then we can amplify that signal and then use that for a radio. This is also done for metal detectors. The detector itself is winding of copper wires, which is basically inductor. And you basically want to set the capacitance such that you're going to get a resonance at a particular metal. That's how we actually can discriminate here. So the metal is present, it changes the effective inductance, and the change in current of, as we go in and out of resonance state will actually sound an alarm. And again, here's what your curve looks like for different resistors for a RLC circuit. Again, if you have the inductance and the capacitance set, you will have a resonant frequency about 10 to the 7 radians per second. You can actually do those calculations. But we notice as the resonance gets greater and greater, we're doing the same thing that we did with the driven harmonic oscillator. This curve is similar to that. With a driven harmonic oscillator, as your damping force becomes greater and greater, this curve becomes flatter and flatter. For an RLC circuit, as you reduce the resistance, this peak becomes sharper and sharper. You actually discriminate over a narrower and narrower bandwidth. And that's very important for radios, that you want your resistance to be balanced, so you will only grab the frequencies. The bandwidth that you grab will only be the frequencies that you want to amplify.